Hello and welcome to yet another lecture on basic electrical engineering, paper code ESEE 101. Myself, Prathita Roy, Assistant Professor of Dr. Sudhir Chandra Institute of Technology and Sports Complex, Department of Electrical Engineering. Today, my topic is starting and speed control of induction motor. Lesson objective. After the end of this topic, students will able to understand the concept of different starting and speed control methods of induction motor. So we are now starting and speed control of induction motor. So starting of induction motor. So why a starter is needed in case of an induction motor? So it is clear that in case of the induction motor, or we can say that the stator, or its, or we can say that the starter are generally means that it is some device that helps a machine to start, which is not self-starting. But in our previous discussion, we have already seen that three-phase induction motor is a self-starting motor. So the function of a starter in case of the three-phase induction motor are different. So the starter is not used in order to start in the three-phase induction motor. Or other words, we can say that the purpose of a starter in case of the three-phase induction motor is to restrict the starting current within a safe value, not to provide the starting torque. So the main purpose of connecting a starter in case of a three-phase induction motor is to restrict the starting current within a safe value, because we know all the insulations that are provided in a motor is generally given, or we can say the insulation is given by considering the running rotor and the stator current of the motor. So during the starting, if the starting current is very high, it can burn down those insulations. So in order to restrict this, or in order to restrict the starting current within a safe limit, the starter is given in the induction mode. So the starters, that is for the squirrel cage induction motor, are classified as direct online, that is DOL starter, star or delta starter, and auto transformer starter. So first we will start with DOL starter, or direct online starter. So this is the general pictorial view of a direct online starter, and it is clear that in this method the starter is directly connected to the main power supply, and the current that is drawn by the motor, depending on its design class, will be from 5 to 7 times the normal current rating. Since this amount of current flows only for a short period of time, it will be not damage the squirrel cage motor, but it may cause undesirable drop in supply voltage, power factor, and subsequently affects the performance of other equipment that is connected to the supply. For this reason, the supply authorities limit the size of motor up to 5 horsepower, which cannot be started by this starter. So, a direct online starter that is consists of a contactor having four normally open, that is called the NO contacts, and it is energized or an energizing coil, that is also known as this one, the no volt coil. That is the energized coil. The function of this coil is to keep together the normally open contacts when the starter is switched on. In case of the power supply fails, no volt coil de-energized and the circuit is opened. The motor will not start automatically if the power supply is resumed, and starter has to be switched on once again. Two push buttons, on and off buttons, are provided on the starter to start and stop the motor. So, to protect the motor against overload, thermal or magnetic overload coils are connected in each phase. This is the general motor, and this is the stop, and this is switch, this is the start button. No voltage coil. The three-phase supply RYB is given to the motor. This is the holding contact, and this is the trip bar, and this is the overload relay. So start condition. On button of starter completes the circuit of the no volt coil. When the start button is on, the no voltage coil has completed the circuit. Holding contact comes to this position, and the no voltage coil has completed the circuit and it is energized. The four NO contacts are brought together by the bar connected to no volt coil, and the motor begins to start. Means when it is given in the start position, this particular coil gets energized, and the supply that is directly provided to the motor, which in turn energizes this energy. When the coil gets energized, the motor gets started. Stop condition. The stop condition of motor, that is the off push button that is pressed, which is in turn that de-energize the no voltage coil and opening the main contacts. When this coil gets de-energized, it opens the main contacts, and which means the motor is in stop condition. When it gets energized, it will hold the contact in this position, and the RYB supply is given to the motor. Means the motor is in operating condition, and when it is get stopped, so it gets de-energized, and it is, and the RYB phase get opened, and the motor now in off condition. So another is the star delta starter. So this method, this is the general pictorial view of star delta starter, where L is stand for line conductor, N is that stand for neutral conductor, F1 is the fuses, F2 is the thermal overload cutout, A1 is the main contactor, K2 is the delta contactor, K3 is the star conductor, and M1 is the three-phase motor. That all we have seen, K1, K2, K3, F1, F2, M1, L1, L2, L3, and the neutral. So this method is used for the motors that are designed to operate with delta connection. The motor that are designed to operate with delta connection for that particular motor. This method is generally used. The components normally consist of three contactors, an overload relay, and a time yarn for setting the time in the start position and starting position. The phases of the stator are initially, that is, start connected using a relay switch, that is A3. Once up to a particular running speed, a double thrown switch, that is K2, a double thrown switch, that is K2, changes the winding arrangement from delta from star to delta, whereupon full running torque is achieved. In this method, the starting voltage across each phase is PL by root 3, that is line voltage by root 3, and thus the starting current is lower, which leads to the smaller starting torque. As the voltage is reduced by PL by root 3, the starting current gets reduced and also leads to a smaller starting torque, which is because it is start. Such an arrangement means that the end of the stator winding must be brought to termination outside the casing of the motor. The stator is provided with overload and underload voltage. The starter, that is provided with overload and underload under voltage protection. The starter is provided with overload and under voltage protection devices. So this is the start configuration and this is the run configuration. Start with start. This is the start configuration, means it is start with start and running configuration of the rotor winding. When it is started, it is start connected. When it is in the running condition, it is delta connected. So in case of the start connected, the phase voltage is equal to line voltage by root 3. That's why we can reduce the current and also the starting current and also the starting torque. Hence, the received starting current is about 30% of the starting current during the direct online start, and the starting torque is reduced to about 20%, 25% of the torque available at DOL start. This starting method only works when the application is light loaded during the start. If the motor is too heavily loaded, there will not be enough torque to accelerate the motor up to speed before switching over to delta position. Means it is start at start connection and during the running it is moved switch to delta connection. When starting off, the load torque is low at the beginning of the start and increases with the square of the speed. When reaches approximately 80 to 85% of the motor rated speed, the load torque is equal to the motor torque and the acceleration ceases. To reach the rated speed, a switch over to delta position is necessary, and this will very often result in high transmission and current peaks. In some cases, the current peak can reach a value that is even bigger than for a dual start. Application with a low torque higher than 50% of the motor rated torque will not be able to start using start delta starter. Another is called the auto transformer starter. This is another is called the auto transformer starter. And this is another starting method of reduce the starting current and starting torque to start delta starting, where this starting method needs 3 wires and 3 terminals on the motor. Auto transformers are generally equipped with taps at each phase in order to adapt the starting parameters to the application starting requirement. During starting, the motor is connected to the auto transformer taps with the star and the auto transformer contactor get closed. The motor is under reduced voltage. The torque is reduced at the square of the applied voltage. When the motor reaches to 80 to 95% of the nominal speed, the star contactor gets open. Then the line contactor closed and the auto transformer contactor gets open. The motor is never disconnected from the power supply during starting and reduce the transient phenomenon. Taps of the auto transformer. This is a general auto transformer connection where 80 transfer auto transformer and 1, 2, 3 are transfer switches. So the taps on the auto transformer allow for selection of motor with 50%, 60% or 80% of the current in rush seen during a full voltage start. The resulting starting torque will be 25%, 42% and 64% of the full load voltage values, as will be current drawn on the line. Thus, the autotransformer that is provided the maximum torque with minimum line current. In this method, quite less current is drawn from the supply as compared to previous methods, but the extra equipment is still required. On the other hand, the starting torque is small as a result of low amount of voltage at starting instant, so this method is not useful for high inertia loads. So this is the pictorial view of auto transformer starting. Another starting method of slip ring induction motor that it is given that if it is necessary to start a three-phase induction motor on load when a wound rotor machine, also known as slip ring motor, will normally be selected. Such a machine allows an external resistance to connect it to the rotor of the machine through slip rings and brushes. A three-phase rheostat it is connected in series with the rotor circuit through brushes. At startup, the rotor resistance is set at a maximum, but it reduces as speed increases until eventually it is reduced to zero, and the machine runs as if it is a cage rotor machine. By inserting external resistance in the rotor circuit, not only the starting current is reduced, but all same time starting torque is increased due to improvement of power factor. This is the starting of slip ring induction motor with variable resistance, and this is the starting of slip ring induction motor with fixed resistance. This is the variable resistance, and this is the fixed resistance again. So L which stands for line conductor, N it is neutral conductor, F1 fuses, F2 thermal overload cutout that all are given here, and Ki is the main conductor, K2 main conductor, and K2 is the resistance circuit conductor, and Ri is the starting resistance, and Mi is the three-phase. Mi1 is the R1 is the starting resistance, and M1 is the three-phase motor, and it is all seen here in this figure. So another is the soft starting. When starting an AC induction motor develops more torque than it is required at full load speed, the stress is transferred to the mechanical transmission system, resulting in excessive wear and furniture, failure of chains, belts, gears, mechanical seals, etc. Additionally, rapid acceleration also has a massive impact on electricity supply. Changes with high inrush current drawing plus 600% of the normal run current. The use of start delta only provides a partial solution to the problem. If the motors slow down during the transition period, the high peaks are repeated and can ever exist direct on line current. This is the comparison of the current drawn by dual starter. This is the dual starter current, and this is the start delta starter current. And also this is the soft start method. And it is seen in case of the soft start method, the starting current is very less compared to the other two methods. A soft starter is a solid motor starter that is used to start or stop a motor by notching the voltage waveform, thereby reducing the voltage to each phase of a motor and gradually increasing the voltage until the motor gets up to full voltage or speed at all at a fixed frequency. The profile of increase of voltage depends on the application. The voltage is reduced and controlled by the pairs of back-to-back silicon converter rectifiers, that is SCRs, which are a type of high-speed thyristor, a soft starter that takes place of a contactor and can also take the place of an overload relay in a standard motor starting application. So this is a pictorial view of comparison of starting current, or say comparison of the current drawn by DOL starting, start delta starting, and soft start method. This is for DOL starting, this is for start delta starting, and this is for soft starter method. Current versus time speed characteristics. Current versus time speed characteristics. So in general, there are two reasons to use a soft starter. The power distribution network may not be able to handle the inrush current of motor, and the load cannot be handled high starting torque. As a result, the motor utilizes around 600 to 800% of the full load current to start. This current is referred to an inrush current or lock rotor current. If a large motor is on similar power distribution network or a generator system, this inrush current can cause the system voltage to dip or to burn out. So that can cause the problems whatever else is connected to the system, such as computers, lights, motors, and other loads. And the problem is that the system may not even be able to start. Another problem is that the system may not even able to start the motor because it can not source or supply enough current. Most industrial business run during the day can be fined or charged extra, that is the maximum demand charge during the peak uses time for large transient caused by the large horsepower, that is kilowatt motor starts up. So the maximum demand changes can add up very quickly, especially if the motor needs to be started multiple times during any given day. The inrush current can be controlled one of the two ways: with a soft starter, either with a current limit, or reduce linearly with the reduced voltage. So there is a comparison between the different starting method. One is called the direct online starting. There are three-phase motor with low to medium power rating, three conductors to the motor, high starting torque, high current peak, voltage A, one simple switching device. For start delta starter, three-phase motor with low to high power rating, six conductors to the motor, reduce starting torque, one-third of the nominal torque, high main loads due to current peak during switchover from start to delta, high maintenance, high mechanical stress due to torque surge during switchover from delta to start. Two or three switching devices, more maintenance are required. For the auto transformer starter, lower relative cost, that is cost about 66% of similar size solid state starter, includes solid state motor protection relays and vacuum contactors. Disadvantages, that is, includes its non-continuous acceleration and inflexibility. Starting method of using external resistance using induction motor, that is, additional resistance is used only for starting. Resistance is rated for intermittent duty, that is, resistance is rated for intermittent duty. Resistance is to be decreased in steps and the motor speed increases. Finally, the external resistance is to be completely cut out. Additional cost of the external resistance is to be incurred. Decrease of starting current along with increase of starting torque, both being advantage, only used in case higher starting torque is needed to start induction motor with high load torque. So for the soft start up, three-phase induction motor with low power rating, three conductors to the motor, variable starting torque, no current peak, no torque peak, negligible voltage drop, peak or drops, you can say, one simple switching device, optimal guided soft top, spot, protective function, etc., and zero maintenance are required for soft startup. So another part of today's discussion is the speed control methods of induction motor. So an induction motor is particularly a constant speed motor. That means for the entire loading range, changing speed of the motor is quite small. Speed of a DC shunt motor can be very easily with good efficiency. But in case of the induction motors, speed reduction is accompanied by a corresponding loss of efficiency and poor power factor. As induction motors are widely used, their speed control may be required in many applications. Different speed control methods of induction motor are given there or are applied. First one, induction motor speed control from stator side, that is by changing the applied voltage. So we know the torque equation of an induction motor is given by that equation. So when the rotor resistance R2 is constant and you see S is very small, so this portion Sx2x squared is this portion is so small that it can be neglected. Therefore, the torque becomes proportional to Se2 squared, this portion. But E2 is the rotor induced EMF and E2 is proportional to V. So thus the torque that is become proportional to S squared, which means if the supply voltage is decreased, the developed torque is also decreased. Hence, for providing the same load torque, the speed increases with decreasing voltage and thus consequently the speed is decreasing or decrease. This method is the earliest and cheapest, still rarely used because large large change in supply voltage is required for relatively small change in speed. Large change in supply voltage will result a large current, large change in flux density. Hence, this will disturb the magnetic conditions of the motor. So this is called the by changing the applied voltage, how speed can be controlled, the torque can be controlled. So by changing the applied frequency, it's the second portion, that is by changing the applied frequency. We all know that synchronous speed of a rotating magnetic field is given by Ns equal to 120 F by P in RPM per P. F is the frequency of the supply and P is the number of stator poles. So hence the actual speed can be calculated by N equal to Ns into 1 minus S, that is known to us. However, this method is not widely used. It may be used where the induction motor is supplied by a dedicated generator, so that the frequency can easily be varied. By changing the speed of the prime mover, we can easily vary the frequency. Also, at lower frequency, the motor current may become too high due to decreased reactance, and if the frequency is increased beyond the rated value, the maximum torque developed falls while the speed rises. So third one is the constant V by F control of induction motor, voltage frequency control, that V by F control. So this is the most popular method for controlling the speed of an induction motor. In this method, if the supply frequency is reduced, giving the rated supply voltage, the air gap flux will begin to saturate. This will cause excessive stator current and distortion of the stator flux wave. Therefore, the stator voltage should be reduced in proportional to the frequency, so as to maintain the air gap flux constant. The magnitude of the stator flux is proportional to the ratio of the stator voltage and the frequency. Hence, if the ratio of the voltage to frequency is kept constant, the flux remains constant. Also, by keeping V by F constant, the developed torque remains approximately constant. This method that gives higher runtime efficiency. Therefore, majority of AC speed drives employ the constant V by F control or variable voltage, variable frequency control method for the speed control. Along with wide range of speed control, this method is also offers soft start capability. So this is the most important and commonly used method that is known as V by F control of induction motor in order to control the speed of an induction motor. So changing the number of stator poles from the equation of the synchronous speed, it can be seen that the synchronous speed and hence the running speed can be changed by changing the number of stator poles because N is equal to 128 by P. Thus, this method is generally used for the squirrel cage induction motor, as squirrel cage rotor adapts itself for any number of stator poles that we have already discussed. Change in stator poles is achieved by two or more independent stator windings, wound for different number of poles in same slots. For example, a stator is wound with two three-phase windings, one for 4 poles and other for 3 poles. For the supply frequency of 50 Hz, synchronous speed with 4-pole winding is connected is using the formula of Ns equal to 120 F by P. This 120 into 50 by 4, it is 1500 RPM. Synchronous speed when the 6-pole winding is connected is 120 into 50 by 6, that is 1000 RPM. So it is seen that changing the number of stator poles, the speed can also be changed. So speed, another part is the speed control from the rotor side, that the rotor rheostat control. So this method is only applicable to slip ring motors, as addition of external resistance in the rotor of the squirrel cage motor is not possible. So additional of external resistance for the rheostat can be applied for the slip ring induction motor that we have already discussed in our previous lecture. That in case of a slip ring induction motor, we can add an external resistance and we can control the speed by using that rheostat, rotor rheostat control method or the external resistance method. So another is the cascade operation. This is the pictorial view of the cascade operation. So in this method of speed control, the two motors are used, one and two, that is motor A and the motor B. Both are mounted on the same shaft. This is the shaft. This is the shaft, and both motor A and motor B are mounted on the same shaft, so that the both can be run at the same speed. So both the motors are mounted on the same shaft, so that both the motor can able to run at same speed. One of the motor is fed from a three-phase supply. So motor A is the three-phase supply that we are obtaining. So motor A is feeding from a three-phase supply. It is clearly seen in this picture. And another motor is fed from the induced EMF in the first motor via slip rings. This is the slip rings, and motor B is feeding from the motor induced EMF in the motor A via slip ring. So this is the arrangement that is seen, that two motors are connected to a common shaft in order to maintain the same speed, while motor A is fed from the three-phase supply and the motor B is fed from the induced EMF of the motor A via slip rings. So motor A is called the main motor, and whether the motor B is known as the auxiliary motor. So N-S1, it is the frequency of motor A. N-S2 is the frequency of motor B. Speed, that is called the speed, and P1 is the number of poles of the motor A. P2 is the number of stator poles of the motor B. F is the general speed of the set and same for both motors, and F is frequency of the supply. So sleep of the motor A, rather than written it as a frequency, we can write that this is the sleep of this is the speed of motor A, and this is the at synchronous frequency, and this is the speed of motor B at synchronous frequency in S1 and in S2. So sleep of the motor A is S1 is NS1 minus N by NS1. Frequency of the rotor induced EMF of motor A, that is F1 equal to S1F. Now, auxiliary motor B is supplied with the rotor induced EMF. Therefore, N is equal to 120 F1 by P2. Just putting the value of F1, that is 120 S1F by P2. Now, putting the values, S1 will be S1 minus N by NS1. So, N is equal to 120 if N is 1 minus N by P2 N is 1. Just putting those values in this equation, the values of slip, we will find the value of N is 2. So N is 1, that is at synchronous frequency, the speed of the motor, first motor, and N is 2 is the speed of the second motor. So at no load, the speed of the auxiliary rotor is almost same as it is the synchronous speed. So N became at no load condition. So the speed of M is equal to M is 2, the auxiliary motor speed. So from therefore the above equation, it can be obtained that speed N equal to 120 F P1 plus P2. So with this method, for different speed can be obtained. When the only motor A works, the corresponding speed is Ns1 equal to 120 F by P1. And when only the motor B works, the corresponding speed is Ns2 equal to 120 F by P2. If cumulative, if cumulative cascading is done, the speed of the set is n equal to 120 F by P1 plus P2. If differential cascading is done, then the speed of the set is n equal to 120 F into P1 minus P2. 120 F by P1 minus P2. So another is by injecting the EMF in the rotor circuit. In this method, the speed of an induction motor is controlled by injecting a voltage in the rotor circuit. We are injecting a voltage in the rotor circuit. It is necessary that the voltage being injected must have the same frequency as of the sleep frequency. However, there is no restriction to the phase of injected EMF. If we injected EMF which is in opposite phase with the rotor induced EMF, the rotor resistance will be increased. It is clear. If we injected the EMF in same phase with the rotor induced EMF, the rotor resistance will be decreased. It is clear. For the first case, it is summing up and the voltage, and for second case, the voltage is subtracted. Thus, by changing the phase of injection, injected EMF speed can be controlled. The main advantage of this method is a wide range of speed control, that is above normal as well as the below normal can be achieved. So today we have seen the different starting method and speed control method of induction motor. Thank you.